Hello. Hello.
لا لا يلا.
Okay, I'll start. Okay.
It's a pleasure to welcome all of you back after the Valentine's Colloquium last week. And things have subsided to normalcy at TIFR. And I think um, what um, what I want to do is I want to tell once again for all the members in the institute, please attend the Colloquia series. It's a very important place for all of us to grow together. And the more you come, the more you sort of have an exposure to all the different facets of science going on in the institute. So even a 30-minute visit trip to AG66 is good enough, but show up and see what's going on. So today we have colloquium from one of our own, a new faculty member who has joined us in almost 1.5 years now. And this is Dr. Suvodip Mukherjee. And Suvodip actually did his PhD from Ayuka, not very far away, and with Professor Tarun Shorodip. And in his PhD, he looked at physics beyond the isotropic cosmological model. And this is something that has really come up in the last 10, 15 years. There is, of course, deep interest in the institute, about this problem. But after finishing his PhD in 2016, he moved as a joint fellow at the Lagrange Institute, which is in Paris. And the other one is a position at the Flatiron Institute in Flatiron Institute in New York. I'm sorry about that. And mostly Shubhadeep has been sort of involved in looking at data analysis and theory developing, protocols to go hand in hand together to explain all sorts of very exciting astrophysical phenomena. So he continued this postdoctoral work as a GRAPPA postdoctoral fellow in University of Amsterdam. And then he went to the Perimeter Institute as a postdoc, and he sort of had a 1-year stint there till 2022. In May 2022, he joined our institute. So today, Shubhadeep is going to talk about snippets of multi-messenger astrophysics and cosmology bucket list. So Shubhadeep.
Which means I have to say this again. So thank you very much for introducing me, Jyotishman. This time I'll change it a bit. So it's a great pleasure to talk in the NSF Colloquium. So this is one of the very first experience I had after I came to TIFR, where people from across different branches in science, mathematics, computer science comes together for this particular kind of colloquium. So when I was asked to give a talk, I work in those topics, and I really do not know what to start with to connect with biology, chemistry, physics, mathematics, computer science. So I want to open my slide with and start talking about possibly the only common thing between us is our calendar. When I say about our calendar, I really do not mean to tell about all our daily lives and whatever we are doing for last 1 year in TIFR. But what I like to talk about is our cosmic calendar. That's possibly the place where actually unites all of us of what we are doing under NSF, mathematics, computer science, and so on. So this is the calendar which shows you if at the 00 hour on 1st of January of any year, Big Bang happened, the universe started. And I put all important incidents one after the other. Then typically, this is the calendar you will end up, where human in last 100 years is like 0.2 cosmic seconds. So in some benchmark points in this calendar is that, as I said, something around here, if the Big Bang happened, our own galaxy, Milky Way, has formed sometime mid of this cosmic time, we call. And in the last 1 month of December, a lot of things which has happened, which we are studying. So long story short, the common thing is, as an astrophysicist, I look up in space through telescopes. And when you are studying other branches of physics, you are practically exploring all these different months through different kind of observational probes. Yeah. Okay. And I think this really unites us in some way. Why within the framework of NSF, we want to hear these different kinds of talks at some point or the other. But now let's start to go deep in this first 8 months of cosmic calendar, which practically may be related to my field of research and what we do in our department as well. So the first 8 months of our cosmic calendar can be shown by this cartoon diagram, where now this tells you how our universe have possibly started, evolved, and what it is today. Everything is not yet confirmed from observations. It's a story where part of it is confirmed by observations. And all these informations we have gathered mostly until now through electromagnetic observations across different bands. So if I want to give you a brief history of cosmic time in less than a minute, what I will tell you, you possibly have heard this in different way or the other for every cosmologist, astrophysicist gave you a talk and in this forum. It's about, okay, we have a scenario where Big Bang happened, who knows what it is? We have just put it there, we still don't know what it is. We have an evolution of the universe, and when the universe was about 400,000 years old, we formed the first atoms in the universe. Some lights comes out of it, and we call it the cosmic microwave background observations, something which is a little bit benchmark in this particular observational history. Then there's an epoch when there is not much stars, not much galaxies, universe was pretty much dark, not boring. If you can really go there, you can learn so many things, but we have not yet observed it. So I will tell you, it's still a place where data needs to touch and tell the truth. Then comes the epoch where first galaxies starts forming. They start emitting light, and the atoms which has formed here starts breaking. And this process is ionization for all of us, except astrophysicists and cosmologists. We have reionization. Why reionization? Because it was ionized before, we form atom and we again break them. So the word reionization appears like that. So now we have formed the very first stars, started, and this is the epoch. Again, you have possibly heard talk from several people in TIFR. We have like Girish and all who are working on this. We have some observational probe in this side from radio observations. We are planning to do exquisite measurement in this particular epoch in the next 10-15 years. And then comes the later part of the universe, which is the low redshift universe. Again, you can see them from different galaxies, supernovas. All stars you see, some of you have an ambition to let's map them in all possible bands I can with the highest angular resolution possible with best sensitivity. This is the game we all are playing and will play for next few decades. This observation has played a major role, and what has happened, this is another map of the low redshift part of the universe. So if I now tell you from this side, back in 90s, we made the first measurement of this with a poor angular resolution. Got more money, improved the resolution and sensitivity. Same sky, better resolution. More money, even more channel, better resolution, we came to this. This is not the end. I'll show you, we have many efforts ongoing to map the cosmic sky in the microwave region and get the physics out of it. It's neat. That's why you are going for it. Same story, low redshift observations. You observe galaxies now. Individual point sources, you start observing them. And these, again, this is one of the map from 2M++. And it goes without saying, this has really played a major role in writing what is called as the standard model of cosmology. It's standard model or not, we'll go to that debate later. Let's talk it best fit model of cosmology. Given all this data I have shown you, possibly you have heard again this statement multiple times. We have a expanding, accelerating universe, out of which 95% we don't know in a standard model. 5% we only know, which is our very own terrestrial matter kind of thing we observe. Remaining around 27% is dark matter, and remaining everything is dark image. This pie chart has evolved, not significantly in last 20 years. But the point is, how much have we really understood of our this very favorite best fit model called lambda cold dark matter? Okay, lambda is this part which is causing the dark energy part, the acceleration, cold dark matter, and remaining we have not written because we assume we know it very well. So putting it this way, so now the question comes that, okay, if this is what all we have understood from electromagnetic observations so far, what is really missing in this picture? Can we go and probe the universe deeper and better? So let's try to understand these two words a little bit more. Why deeper? I started with the cosmic calendar and told you job of the cosmology / astrophysicist is to go look up and see as many galaxies as we can. As many galaxies as we can, up to go further out. That's what you would like to do. In simple way, if the object is very far away, we measure its redshift. So in simple word, I want to go to very high redshift universe. If I go to very high redshift universe, like any branches of science, if you are really digging deeper and deeper as a function of time of its evolution, you start mapping the evolution of the universe. So let's start with one single agenda. Our job or our interest is to understand the evolution of the universe. Having said so how do you do that? You would like to use a probe which can actually go and measure something deeper and something which can do a good job. If I measure something which is extremely contaminated, then better I need to come up with another way to clean it. So a method which needs least cleaning possibly is a neat way to go up to high redshift universe, if it exists. We are not lucky to have it. Whatever we want, we don't have it. If nature is lucky enough to give it to us, we can use that. First is nature and second is engineers who can build those telescopes or detectors for us to actually make us talk with the nature. And this happened. I'm sure you have heard plenty of talks in this institute. We have observed gravitational waves, and gravitational waves opens up a new window / observational probe to the universe, which can make it possible for us to go deeper and better. My remaining talk will be a lot talking about why is it better and how deep we can go, and what is the outcome of doing all those. Before that, I'll pause and take any questions if at all exist. Okay. So that means what you would like to now understand, I told you, this is the price of the universe we have observed from galaxies. This is the part of the universe we have observed from cosmic microwave background. In between, there are several epochs which we have not yet really understood / measured from data. And here comes the 95% of the universe which are yet to be understood. We only given them name and the word dark to show our ignorance. Okay. So when I now start talking about gravitational wave, I didn't talk to you about electromagnetic probes at all. Here you are like electromagnetic waves comes in a huge spectrum. You see radio to gamma ray, talking about like that. We exactly do the same thing for gravitational wave. Let's at first start with the spectrum of gravitational waves. In the left hand side, you are seeing high frequency end. In the right hand side, you are seeing the low frequency end. Here is something like kilohertz. Here it is something like 10 raised to minus 17, 10 raised to minus 18 hertz. Okay. At the extreme high frequency, the objects which are interesting are typically small in size. When you go to small wavelengths or large small frequencies or large wavelengths, you're talking about big size objects. It's the first discrimination. Let's do that this way. Then let's start talking about what is these particular sectors that we are going to measure. When you're talking about high frequency, let's talk in the range accessible from ground, where earthquakes are not that important. Above 10 Hertz, we can do some nice science. And these are the objects like binary neutron stars or black holes. Why the word binary? This is very interesting, because when I talk about gravitational waves, you need a change in the quadrupole moment of the system. The system is isotropic, you're not going to emit gravitational. So whatever it is, even if it is a single object, if it emits, if it has some net quadrupole moment which is changing with time, I'll get some gravitational wave out of it. So at the very high frequency end, we are interested in objects of such kind, which are typically few tens of mass of binary black holes, few neutron star black holes, and if at all exist, some of the sources of cosmological interest as well. As you go to little bit high frequency, low frequency, now you're in the millihertz range. Here the sources are like supermassive black holes of million solar mass. So I move from here to here by almost 4, 5, 6 orders of magnitude, and it's typically same in the mass I'm talking about of the order. Supermassive black holes I'm talking about. These are the sources exist, and we would like to detect, we can detect them in this particular range. I'll come in the top axis later. Next is pulsar timing array. Is of course you have heard from Goppu on this a lot, and there are several talks on this. I mean, NCRS played a major role in making this discovery. We have heard and results from PTA and signatures of supermassive black holes in this. And this extremely low frequency wave, so these are like very, very big objects. You possibly don't expect such big objects in the universe which are of astrophysical origin. You cannot have one object which is of the whole size of the universe, right? So this is the size which is of observable universe. So what can be emitting gravitational wave there? Things of typical cosmological origin. So that first slide, when I told you that Big Bang has happened possibly, we don't know yet, signature of that will be imprinted here. Because if it has happened in the universe, and it should be imprinted at all scales, including the largest scales. And that's what you would like to go behind the world. And now the question is it possible to do it? This is our ambition. This is what we would like to do. We have a science goal. We have an observable probe. How will we measure it? And that's why the engineers have entered. Thanks for decades of work in the extremely high frequency gravitational waves, we have ground-based detectors. I have listed a few of them here. LIGO Virgo Kagra, currently operational. LIGO India, which is be operational soon. Proposed telescopes such as Cosmic Explorer and Einstein Telescope. Space-based detectors. Now these are in the millihertz range. These are not something we can detect from Earth. So you want to go in space or somewhere it is quite enough to be detected. So what's the ambition? We are going to launch detectors. Not one of them, one detector won't do much. We need to see the signal in multiple detectors so that we talk them. We say it is astrophysical / cosmological origin and not your noise. So you need to save many of them. So that's a system of 3 detectors will be in space, floating around and trying to detect gravitational wave if we can. It's still a challenge in the engineering level. To trust on engineers and scientists, government has asked the team, can you show us a pathfinder and show that it is going to work? And so we have the main please.
So what's the proposed technology there? It's on interferometry.
It's interferometry.
It is interferometry.
Interferometry, but floating object. My job is everything is floating, but I want to control each of them. Each of them are floating in a triangular shape. So I want to make a control system of the configuration where I do not exert any additional force to perturb them. They are floating.
So the interferometer is between the
Right.
three.
Yes, that's correct. Kilometers, yeah. Complicated, yeah. The technology is way more complicated. So we are still pushing the technology to the level where this launch can happen by 2036, 2037. The latest news, of course, many of you possibly have already heard, LISA has got a formal adoption from ESA. That means, yes, go for it. This happened exactly 2 weeks back, which is a great news. So, and these two are yet to be funded formally. Proposals are ongoing. These you know that they are funded. LISA has got its final go from ESA, and NASA. India is not a part of it in the technology side, but several of us are part of it through the science/data analysis. I will not talk about PTA because I don't qualify to talk about that. I'm sure you have already heard about it. I don't work on it. I do not talk about it. Another thing which comes at the very, very low frequency gravitational waves is the one from CMB. So right now we have now formally, not through money, but through in kind, a part of CMB-S4 collaboration. So TIFR is a part of CMB-S4 collaboration, us and NCRA. Aim to detect primordial gravitational wave of the universe. We also have Simons Observatory from the Simons Foundation, and is funded, is going to be operational, and these two are practically a factor of 2 to 3 better than each other. Okay, so that means 10 raised to minus 17, 10 raised to minus 18 hertz. Minus 18 hertz. Easy thing to remember is size of the observable universe. Oh, so good. BICEP is at the level 0.0. So okay, so technical term. When he mentioned about the experiment BICEP is an experiment which tried to measure gravitational wave. What do you measure? You measure the amplitude. This amplitude is popularly written in as a notation called R. So if I say R from now, it is the amplitude of gravitational wave with respect to scalar perturbations. Okay. Forget about the later part. It's the amplitude of the gravitational wave. Amplitude measured or at first claimed by BICEP was 0.2. They measured the signal correctly. The corresponding inference that it is gravitational wave is wrong. Why? We have other contaminations which they didn't take into account, or put it this way, couldn't take into account because a mission like Planck was not there. See, you want to see signal coming from here, and you want to see, you have things over here. We call it foreground. For experimentalists, you have background. For cosmologists, background is the signal, and we have the foreground. Okay? So you need to remove the foreground to make sure you are detecting what you want to actually go for. All right? And that's the place where it was a difficult job. And as Gopu just now pointed out, BICEP made a measurement which was incorrect. Then BICEP did a joint measurement with Planck. Planck had 8 channels. We could improve them. That gave us a number of 0.05, value of R, amplitude. This experiment is going to give us 4 times 10 raised to minus 3. No, it is amplitude. So that's why I said this number is the total amplitude, unitless. Sensor to scalar ratio. I don't want to use the technical. It's just amount of gravitational wave with respect to scalar perturbation. Okay? And this experiment is going to do 5 times 10 raised to minus 4. Yes.
Claimed this, and then the foreground, which turned out to be what they made a mistake for, turned out to
Right.
be old galactic supernovae,
Yes.
big loops.
Right.
So then you need to kind of find a place in the sky where these sort of things
Are not there.
are not there.
That's right.
But you have no guarantee there is such a place in the sky.
Good. Very good. That's why we are now, that's what the job of CMB-S4. What is the, so you combine your best folks to do a good job. What CMB-S4 is doing, getting all the good telescopes together. South pole, act pole, bicep, everything together. So CMB S4 will be a combined experiment which will go deeper in a small sky patch with experiment like SPT, South Pole Telescope. See, you cannot see everything and also go deep, right? I mean, you just don't have bandwidth. So you are limited by this. So SPT will do small focus search. Bicep will do a little bit broad sky. Combining these two is the combined effort which we like to push. How far we can go with this? Our current estimate tells us that we may be a factor of 2 off because of the foregrounds. But again, there are, you possibly already know, there is an experiment called Lightbird. It's a Japanese effort, Japanese/ plus Europe, which aims to detect primordial gravitational wave with around 15 frequency channels.
No, my question's a little bit more. So you go to 10 to the power minus 3 in tensor over scalar ratio.
Yeah.
And you combine everything and you finally have a 5 sigma detection.
Right.
How do you know that's still not due to an old supernova remnant in the galaxy?
Color of the emission. So what we would like to measure, if it is CMB, is coming from a black body. If it is coming from a black body in the low frequency regime, it's pretty flat. What we would like to measure is the emission of light, polarized light, at different frequencies follows a different color or not. That's the game we want to play. So if I give you 2 channels and I give you 5 unknowns, you know what you want to do, you can get whatever you want. But if I give you 15 channels and you have 15 unknowns, you can fit all of them together. And that's the place we are going for. We will never be able to say that there is no contamination. We can only say we know there is no contamination up to this level, and that number I'm telling you is of the order few times 10⁻⁴.
You don't mind me
Sure,
asking
please.
one more?
Yes.
When Bicep made the claim, one of the reasons everyone everywhere was excited was because the strength of the R they measured would correspond to the Higgs as the inflaton.
Right. So if you are at Ayuka, if you are at Ayuka in the next hour, we knew it is wrong.
Okay.
We were not excited. I was in 2014, mid of my PhD time. It happened. I was with Tarun, Sanjit, and everyone. We discussed, this doesn't look good. This seems to be wrong. And then you know the history. Within 2 months, multiple groups have written papers talking about this in great depth. And we know it almost because we are in plot of Planck and we haven't seen it at point 2.
Okay, I request questions to be absolutely at minimum for the next 15 minutes. Thank you.
Oh, thank you. Okay, so this I told you, science case, what we want to achieve, and thanks to the engineers of how will we achieve this. But possibly the question comes is, okay, we'll achieve everything. Now, why should we do that? Why is gravitational wave so special or interesting? The word better, let me justify the word better. So in my simple slide, what I usually do, I give this 4-dimensional explanation of how gravitational wave sounds quite interesting and special. Here is a 4-dimensional vector space projection on a 2D slide. You can imagine how good I can do that job. But still, see, this is redshift. This is time scale of a signal we observe. This is the type of signal we observe or sources, and the typical length scale we observe from this. Okay? 4 fundamental things we usually talk in any branches of science. Except this is the distance for us. What gravitational wave brings us that we can see very far in redshift and or distance with the help of these telescopes. So it is not something you can see only locally, you can see up to very far away. Number 2, the kind of time scales involved, some sources are of milliseconds order, some sources are of days order, and some sources are of years order. All of them governed by the same law of physics, Einstein's theory of general relativity. So you are solid on your physics ground on this axis, and you are hopeful to go this with the help of engineers. Nature is kind enough to give us multiple sources: binary neutron star, binary black holes, neutron star black holes, supermassive black holes. I'm not going to read all the abbreviations, forget about it. But these are the more or less the sources you have. And now comes the length scale or the physics. We end of the day, you're a physicist, you're interested about what we're going to solve. And there usually the length scale comes in. Gravitational wave is a probe using which you can probe physics at length scales of kilometers. I don't need to say anybody about this length scale, to largest scales in the universe, gigaparsec scale. And what does it mean by this? So let's say that I have a source of the gravitational wave measured at some distance. I go very far away. So that means at the cosmological scale, I'm doing physics. I can do cosmology using those observations. How exactly in this source the black holes are forming, that depends on the property of the galaxy. Black holes form from the death of stars. Stars form in galaxies. So the scale over which galactic physics is important gets imprinted / observable, if you can see the host galaxy of the gravitational wave source, on this scale. So this is from gigaparsec to kiloparsec scales, okay, few tens of kiloparsec scale. Then we boil down to stars. End of the day, we are talking about end product of stars if you are not talking about any exotic object, such as primordial black holes. If so, then the stellar properties gets imprinted on the compact objects you are looking at through binary neutron star, binary black hole. It's not an easy job, but it's a job which is interesting to study. I'll just show you some results on this. And finally, when these black holes are coalescing, they're coming nearby, each of them are very heavy, their Schwarzschild radius is typically of the order of few kilometers. So you start exploring physics at a very, very small scale. We cannot put such a big tens of solar mass black hole in our Earth, and we cannot go so nearby any other way. So now you can see the justification of mine why I put that axis of length scale over which physics can be explored using gravitational waves. Depend upon what is interesting to you, whether you are a cosmologist, you are a astrophysicist, or you are in fundamental physics, you possibly have your interesting piece in the gravitational wave observation / data if you would like to look for it. So moving on, so this picture which I have started with, so I'm still in the introduction. I don't know how will I finish, but this picture I have started with where we have an observable probe here, we have some low redshift observations. Now this gets broadened, justifying my word deeper in that statement. With LIGO, Virgo, Kagra, LISA, Cosmic Explorer, Einstein Telescope, we will go deeper and deeper. So we are going to see universe when it is much young. That is with binary compact objects. But we don't see every signal with high signal to noise ratio. Signal to noise ratio is not a very big jargon, so I can stick to it. Whatever we do not see as a huge signal to noise ratio, we put them as background. Let's do that. Or signals which are not measured in phase. As soon as you play that, and if you can measure this, you really can go up to the very first second of the few, 10⁻⁻40 seconds or so of the universe. That's the place of Big Bang, I told you, with 10⁻18 hertz. So if this is where the exact place we are trying to go. So that means if you are going for stochastic gravitational wave background, whole universe is observable to you. So now one can ask me, wait, why not with photons? Come on, they are so easily observable. They are so easily observable because they interact so easily. And universe is not free. You have Thomson scattering, photons will get Thomson scattered. And beyond this, you have the first atoms are forming here. So you don't go much deep, it's very optically thick. We don't ever call gravitational wave thick. No, it's always thin. Means gravitational wave don't interact much with anything else. That is the first place we had to wait 50 years or 70 years since they started to discover the signal. So we can really go deep and measure the signal accurately because it's less impacted by other things. It's less scattered. Having said so, and now because we have all these probes, we have a huge list of bucket lists. Given your fundamental physicists or cosmologists or astrophysicists, you can do gravitational lensing, you can do testing, gravity. signature of dark matter, that is about 27% of the universe, cosmological gravitational wave, yes. No, it's okay. I think I can, okay. Okay, fine, sure. So let me quickly go through it. So we have a list of topics. Let me not read through all of them. I can classify them in fundamental physics, astrophysics, and cosmology. And that's where the interesting part is appearing. In my talk, or any talk of 1 hour, I cannot do a justification in covering all this. So what I'm going to cover is what seems to be an interesting science goal that is deliverable in, let's say, 5 to 10 years timeline, and which has a potential discovery space. New, not only a confirmation, but new discoveries. Of course, there are more fundamental things that are possible with future detectors. I will not talk about it in this time. This means you have a chance to ask me later during the coffee or tea. I'll take questions from you now before I move to the next part. I think I am good.
Don't have high density of certain kind of, okay, for example, black holes. Okay, now what makes you believe that if you go very early on, you'll still have an universe which is transparent to gravity waves?
Good. So we are talking about length scales which are much larger than Planck lenses. That's it.
No,
and
but you aren't you saying that you're going beyond the first scattering, the last scattering?
Yeah. So here, as you go deeper and deeper, your universe density drastically goes up.
Right. So what Z? That's the question.
How far in Z do you go? You can go 10 raised to 8, 10 raised to 9. What calculation has been done, I can tell you that. One calculation, soon after the gravitational discovery made, we ask this question: how much is the scattering? One can show that the amount, so this is done by people like Raphael Sager and Stephen Weinberg, soon after discovery was made. How much is this typical scattering going to happen on the gravitational wave signal? It is of the order 10 raised to minus 43, minus 44. It's weak. And we are going to measure signals of the order 10 raised to minus 20s. So now, how far in density? Because you understand my problem. I only trust up to here. Remaining, none of us know. We can play with, we can add as many epochs of universe as you want, because we really don't know. So I have a free parameter in density. I do not know how to quote it. But yeah, as far as we don't hit the scales of Planck scale, we don't know, or physics itself, we have never tested here in those scales. Classical limit of gravitation is valid. Let's put it that way. Any more question for me? So now, having said that, we have a list of bucket lists, but I'll only cherry pick my favorites, which are possibly be achievable if detectors are operational in the next 5 to 10 years, and which are also interesting, but it's only my bias list. So to start with, I will cover this whole story in terms of redshift. One can take any of these axes, okay? Today in my talk, I am covering this axis. I'm going to tell you how interesting the science are if I go from low redshift to high redshift. So let's do that. And the first thing, which turns out to be an interesting question, is let's make the measurements local enough. It's like, let's know our neighborhood. Start with our locality. Almost redshift 0. And what we have measured for last 100 years, almost 100 years, 1929, is that the universe is expanding. It's called the Hubble law. No more the Hubble law. It's called the Hubble-Lemaitre law. Because Lemaitre has also made a significant contribution, and International Astronomical Union has formally made this law as Hubble-Lemaitre law. This goes to the new students. It was not given credit because it was written in a non-English language. So if you don't write papers which are easily readable, this can also happen to you. So having said so, now let's start with talking about the first step, about the expansion history of the universe. And so about sources which can have some light as well. So why is this question interesting? 100 or nearly 100 years of observations. What turns out to be, when we want to measure our local expansion rate, we know our universe is expanding, and I want to know what is that value. If I use a probe which is very local, I get a value which is different, shown by these blue shaded regions. And if I use a probe which is far away in redshift, I get a different value which is in black dotted region. So this is the CMB measurement which I showed you in the previous curve. And this is the measurement coming from supernova. So I cannot expand by two different local value of expansion rate, right? This is not possible. So either these values are wrong or my physics is wrong. We don't know what is the answer. Nobody knows. This topic is hot and will remain hot. We will keep it hot until we really get some independent measurements to nail it down. Is this just the two measurements? The answer is no. This list is long, very, very long. And as we proceed, maybe 5 years down the lane, I will show you even a bigger list. Okay? Main take-home message is depending upon two different probes, your value of Hubble constant are different at a level more important than your statistical errors and any known systematic errors. Okay? So let me focus on this piece of the work which I have circled over here, which is on the work by us, which have imprinted on the measurement of gravitational wave using, to measure Hubble constant, using gravitational wave source for which there was an electromagnetic counterpart. This was a work done back in 2019, where we have used until now only single bright electromagnetic counterpart gravitational wave source. It's called as GW170817. Using this observation, so that you can see the relation is very simple. It is a measurement of left hand side with a ratio of these two quantities. What are we trying to measure? We are trying to measure how fast a thing is going away from me with over how far they are. This is the game you are playing. Ratio of two numbers. How fast they are moving. Our favorite technique, all of us, many of us use in our lab science, Doppler shift. Okay, good. Spectrum measure kiya, I take a ratio and I get to the science easily. How do you get distance? Even if you ask me, okay, table distance, I can measure this. If I want to measure there, I need somebody's help. And then somebody asks me, what is the length of that wing of a wall? I am a little bit difficult. I need something to measure it with. Measurement of distance is very difficult in the universe. It's an absolute measurement. As a result, this ratio inference becomes tough. As tough as it takes even 100 years, still we are waiting for an agreement between two different probes. So what's the take home from this particular plot? We have made an inference of Hubble constant from gravitational wave source. This is the posterior distributions on Hubble constant. Let's say this is the best, most likely value, which right now agrees with both the measurements. But in future, this inference is going to significantly improve. Okay? This measurement is going to improve with the help of how many sources? You need to ask this question, right? With one event, I have about 15% error on the value of Hubble. What has been shown here that the main problem is not only about inferring distance, but also about measuring something called as the velocity of the galaxy host. See, you see an object going away. Is it going away because of expansion of the universe, or is it going away because of its own velocity? That's the piece which is over here, and that's very difficult to measure. Ultimately, you see a Doppler shift, which is a combination of both the effects. When you do that, there is a projection of how well this measurement is possible in future. You have how many sources are required as a function of the error. What is the level of precision we need? We need a 1 to 2% measurement. That's the quality cut which is there from CMB/supernova observations and so on. And that we will be able to achieve only by 50 or more, about 60 to 70 sources. And this is tough. Do anybody knows how many such bright stars are there? And we have total about 100 events. Out of that, one. So if they continue the ratio, you know what will happen. Yes. Yes, these are all sources for which you need electromagnetic counterpart. All bright neutron stars. 50 or about with LIGO Virgo Kagra and LIGO India will be only able to achieve around 2.5% measurement. And we plateau there because of the error on peculiar velocity. Right. So that means 1 out of 100 chance, and it is tough. No, you find the host galaxies. So you need a minimum amount of time for which the signal is present and I can catch them. And because you have only one source, GW170817, you always benchmark with that. Our current telescopes are capable to follow it up if it is a GW170817 like events. So the number is 50 or 70. I never quoted my success rate.
No, the question was, can you get rid of the host galaxy velocity, or is it you are assuming that that is also measured?
Very good question. You can never assume it. The problem is, or he is asking that how will you get this peculiar velocity in the first place? You make an inference of it. The way to think about it, how the velocity is coming. Object is falling towards another object because of, I played cricket. So the object is falling towards a heavy object. So if I see a heavy object and I see a small object, I can make a calculation and ask how fast they should move. Little sophisticated way we do it. We calculate the gravitational fall time and you ask how the density field is. We do all these calculations and then you get an inference of the peculiar velocity for this source. And this whole setup is called Borg. It's a name for you, but we can discuss this much later. So the idea is you do a joint reconstruction of velocity field and density field. Because density field tells you how objects should move.
The main reason I was asking is sometimes, depending on the system, the galaxy may be very faint and you might not know the host galaxy.
Right, then you throw them away. That's the problem. It's an inefficient process. And I come there to the very next slides, sources without electromagnetic counterpart. What do you do there? So you have a channel which is very good but difficult to do. So you want 1:100. So do you throw 99 of them? Then why do I do science anyway? When something is difficult, then you spend more time in understanding how to push the boundaries, right? That's what most of us doing all the time. So now what I am going to tell you that let's say I have a distribution of these sources. All these are my black holes I have seen. These yellow dots are my cartoon diagram for black holes in the universe. Are these black holes going to form in a random place? As just now Saurabh mentioned, you do see the galaxy. That means all of us assume there is an underlying galaxy. Galaxies don't form at random places in the universe. Galaxies form in the places where there is more matter. Gravity always is attractive, it attracts more there. And you end up seeing that places where have more galaxies, this is a snapshot of an image from illustrative simulation. Places where I have more galaxies, there the black holes are going to form and not at the other places. So if I now have a spatial distribution of black holes and a spatial distributions of galaxies, these sources, these galaxies can be very good measurement of their redshift, both peculiar velocity and true redshifts together. But that means if I can infer both of their clustering, the spatial clustering of gravitational wave source with galaxy, I can get to a measurement of Hubble constant. That is the place where other black holes for which electromagnetic counterparts are not present can be used to measure that ratio. See, why is it possible? It's very simpler to think about it. I know the distance from gravitational wave, but I don't know the redshift. How am I finding the redshift? I am asking, tell me those galaxies for which the gravitational wave source shows more spatial clustering. That is the redshift you are assigning to it, and we call them the clustering redshift. It is practically this equation again. Instead of seeing an electromagnetic follow-up, you are asking the gravitational wave sources to tell you where the distance is, and the galaxies to tell you what is the gravitational or the redshifts are. And this you can practically do because you have two different observables who are complementary and very good in their job. You can combine them. Gravitational sources are very good measurements of distances. And galaxies which you observe from light are very good probe of redshift or spectrum. So if I can know how to make these two sectors talk to each other, I'll be in a business. This we practically do in any branch of science. We do two independent probes and we do clustering. Is there a clustering happening? Then these two are related. What is the technical term for that? Cross correlation. You do cross correlation of two independent probes and try to find out what is common. Again, this is a summary plot trying to tell you this is the Hubble constant in small h naught. That's a cosmology way of writing actual Hubble constant times 100. This parameter called bias parameter is coming from a paper. So I have to explain this in physics language. Stay with me. This structures how black holes are forming in galaxies, some kind of formational channel history. And this is a redshift evolution of that quantity. We call it the gravitational wave bias parameter. What we have shown here, this is the work done by one of the master students in 2021, where we have shown that based on this cross correlation technique, upcoming detectors such as which are in the galaxy surveys like DAISY, Sphere X, in combination with LIGO, will be a great probe for measuring this quantity. And we right now we have a footing in DAISY as well. I mean, you have heard from Shadab a couple of months back about DAISY. So so these are the techniques or telescopes time which is available to us, and we'll be able to do this science. Just for technical things, Sphere X is another nearly spectroscopic survey. I don't call it spectroscopic because the errors are large, but it's still very interesting and doable for this kind of science we are talking about. Moving on, I have a little time. How much time do I have? You still have 10 minutes. I have 10 minutes. Okay. So I will not hurry, but I will stop in 10 minutes. Whatever we can cover. So yes. SKA.
Up to 100 megaparsec, and they is much better. That's what I vaguely remember reading somewhere.
Much better in what?
To get the Hubble constant, because the mega mesas right now we have few in numbers because of the 21 gigahertz business, but that should be possible with SKA. And there the measurements are very precise because again you are looking for a binary considering the mega mesas going around a supermassive black hole as and they have no systematics because those distant measurements are pristine compared to gravitational wave with lots of uncertainty there too.
Right. The error in the mega measures are large. I mean, like for
down. But with SKA,
yeah, so the SKA in the era of say 2030, 2034. So these numbers are basically 5 years of LVK. So by the time we will go to the era of SKA, we'll have Cosmic Explorer. And these numbers, we are, no, it is going to be really, really interesting to get to the quantity to ask is, which quantity of those measures are free from systematic errors?
Yeah, so this will have other, the cross correlation has inherent problems, which you can't really blindly, you need calibration for this.
No, you do not need any calibration.
We'll talk about that. Anyway.
Yeah, we do not need calibration for cross correlation. Cross correlation is applied straightforward in multiple cosmology analysis. First in 1995 by Daniel Eisenstein. Is very established. Because what do you calibrate? You measure redshift from spectra and you measure a point on the sky as through your PSF. That's neat. Remaining is all asking, why do I see the clustering? So there is no calibration error there, right? And if somebody gives me a good spectrum, I measure the spectrum and I give me a good telescope, I see point the galaxy to one galaxy. That's my job.
Yeah, incomplete sample, but that's a different thing altogether.
Yeah. So we have explored this to quite a good details.
Sure.
So as you know that modeling of measures and all, there are several issues. For gravitational wave, it brings a completely new window. Whether that window will talk about a different Hubble constant or not, that we'll see. But let's try to quickly cover about any question? About this testing GR with gravitational waves. I told you that gravitational wave predictions comes practically from GR. So how do I test GR for a theory which already predicts that? Right? This is a little bit confusing. What we can do is that we can detect gravitational wave signal very nicely from detectors. And we can ask, whatever you are detecting, is it agreeing with the predictions from GR? The left-hand side piece of a measurement is not theory dependent. Measurement is theory independent. As a result, you can ask how well any deviation from this can be measured. And that's one of the efforts which are ongoing to test general theory of relativity using gravitational wave sources. And this is possible in a way which is never been done before, and obviously because gravitational wave was never used as observational probe for this kind of science. What we practically end up observing at very large scales, I'm talking about very large cosmological scales effect, where signal emitted from these sources can be interacting with the space-time and may be distorted as it comes to us. And this is the number we call gamma that we want to measure. This quantity is practically like change in the effective Planck mass with redshift. What we want to do, we would like to measure this quantity in a model independent way. I assume GR or I assume a theory and I get a results. That is not so great if we can do a model independent test. So what Afros has shown is that by combining gravitational wave observations with observations coming from other probes, CMB and galaxy surveys, theta BAO and sound horizon. These are technical terms I know, but for experts will understand, others can ask me. It's basically a combination of 3 length scales. And asking that if the 3 length scales are not matching, that's the signature that your theory is wrong. And this quantity we can now go and measure as a function of cosmological redshift in a model independent way. It's the very first work which made it possible because you now have a measurement at all independent redshifts. There's a shaded region. This is for LVK binary neutron star. This is for neutron star black hole system for LVK. And this is the horizon for Cosmic Explorer and Einstein telescope. So take home message is we are entering in an epoch where maybe in 5 to 10 years down the lane over here and in by 2040s over up to here, we will be able to make a model independent test of general theory of relativity using gravitational wave propagation. Moving on, when and how the black holes form, and I have practically 4 minutes. I would not have much time to talk about this part. We are basically now moving in redshift. You can possibly see now a little bit in higher redshifts because you can talking about black hole formation channels and so on. I will not have much time to discuss this in details. This is a picture showing you what is there in the data. This is the mass of the black hole, this is the luminosity distance. How have we seen the sources as a function of effective spin parameter? This is just in the data. So you don't have to do any additional physics. One can just, this is a project done by one of the, like a first year student, he came and wanted to do some science, he's a local Mumbaiker from TIFR. So I gave him LIGO data and told him, okay, show me what is there in the data. And this is the plot he has made. But what is interesting is we can get some interesting physics already from the existing gravitational wave sources. With about 100 detections, out of which around 42 of them with higher signal to noise ratio, we are in a situation to make an inference of the black hole mass distribution in the universe. Here you are seeing a plot of how many black holes are merging in the universe in every mass bin. This is the mass bins. And in color, you are seeing the redshift. It is still early stage, not a 5 sigma detection. There is a mild hint towards that heavy black holes are turned in more at higher redshift than at lower redshift. And to see something extremely interesting, you don't need to do statistics, right? If something is there, data should speak. What is the, sorry, shaded region? Oh, good, sorry. I should explain this plot. Give me 1 minute at first, okay? So we see more of heavy objects at high ratio. How can I see this already in the data? So this is my source too far away in distance. If the source is far away, it gets fainter, like anything else. I see, and this is the primary mass I have observed. this is the region where heavy mass nearby. Heavy mass emits a lot of gravitational waves. So if they emit, I should see them. And I don't see them. There is no selection function at this place. I should see them. Heavy objects nearby, I should see them. I end up seeing more heavy objects at a larger distance. Remaining is statistics, details, all those things. But this is there in the data. This data speaks that there is a hint towards a little bit more mergers of heavier masses happening at high redshift. What is this peak? So there are two things. One is a fast fall with a kind of a distribution like this, and there's a peak here. There are two main features. This particular shape, we expect if the black holes are coming from stars, they may be following the underlying stellar distribution. When you don't know anything, you start with whatever you know before. We start with some power law form, Cooper mass function, and so on. We make an inference of that. But black holes of all mass, stars of all mass don't form black holes. And what's end up happening, if they're too heavy, they will destroy themselves and throw away all the material. By a technical term, what is called a paired instability supernova. Means they have extremely high radiation photons, and they can cause electron and positron, and they can squeeze in, and then there's a shock and everything can go away. This everything and going away is so powerful that it can throw away most of the materials, ending up having no black hole. So even if I start with a nice distribution, I always kill them here. I see a pile up. And this piling up you are seeing in the data. It is also present. Our inference, this is not yet confirmed, is that this is related to the paired instability supernova mass scale. Theoretically, it has been first done by Hans Bethe, and then 30 years, 40 years of work. Typically, it should exist between 40 to 60, 65 solar mass modulo metallicity of the parent stars. And there's a lot of physics going on this. I mean, we are practically organizing a conference in Leiden. We call it Gravitational Wave Year, which is basically going to talk about this physics. I mean, we hope to have Saurabh as well over there. So let's see. So long story short, I will not go to any much more details, but would like to just mention that this is the beginning of a completely new era. Those who have worked on with metal lines through emission line galaxies are excellent probes of the metals of those. And those can be connected with the black holes if you know the underlying physics which is going on, which is very, very complicated. But these two are independent observational probes. One side, you can measure metal lines from spectroscopic surveys. Several of us are doing that. And the other side, gravitational wave can be distance measured as a function of distance with their mass measured very, very well. And if these two are connected by physics, which you like to model at first and then infer from the data. I think this is a place where I can stop a science case. I will not talk about any new results. Let me just go towards the end. I couldn't talk about the project of Mohit at all. Sorry about that. Which is practically an interesting aspect that there is an intrinsic breakdown of time translation symmetry on gravitational wave signal. I want to throw this word to you. This is something very fundamental. And if you'd like to know from me, ask me during the question session. I will just end there with saying that what in the group we are trying to do, we are touching with gravitational wave data, inference of gravitational wave data from the sources from the signal, masses, distance, and so on. Inferencing of physics from that, astrophysics, cosmology, and fundamental physics, and then connect it with your model that we have started with. And whenever we are lucky enough to use an electromagnetic counterpart or electromagnetic signal of any kind, we don't miss them, we use them. And the coming years are very interesting. Already we have projected plans until 2030 for LIGO, Virgo, Kagura. Most of you already know that LIGO India has been approved by the government of India. Prime Minister has now founded the stone online. This is the design of the site, and on last year, May, he has founded the stone. And there are multiple observable probes opening up in the next decade, now until next decade. So you talk about gravitational wave observations, Gopu talked about SKA, Rubin LSST, we are again a part of LSST Rubin, DAISY, Euclid, the huge amount of observational probes which practically opens up the epoch of doing multi-messenger science in the coming 15, 20 years. And what we are doing, we basically work on all these band of gravitational wave. I am part, I mean, the group and me and part of all these individual collaborations. And I'm not in CMB Simon Observatory, but in CMB S4. And we basically would like to use all this data the best possible way and get science, some of the science which I discussed. There are more to it. These are my group members. Just want to show you about a couple of the undergrad students who are joining thanks to several national initiatives. MSc students who are doing projects, and the TIFR PhD students who are either already working with me as their departmental projects. And it's Lalit who is visiting after his postdoc for a short time. And I'll end here and saying that this all works are done with multiple collaborators across the globe where, of course, we work together. And some of you are part of this meeting which happened a couple of months back, and we are in tune to proceed it towards something useful. That's called the GWEMNU, and looking forward to a useful outcome from that too. So with this note, possibly I will end my talk saying that stay tuned for more data and more discoveries. Thank you very much.
Thank you. Fantastic, Suvodip. You almost gave us a feeling that we were understanding. Okay, more questions. Yes.
I have two questions. One is how earlier people measure the length of the galaxy and how the black hole give it much more precisely.
Good. So the first question is about the length scale. Usually our basic thing in the universe is whatever we do in our lab physics. If an object is very nearby, we will use parallax trigonometric techniques to measure the typical size. But inferring of a typical size, physical size, is difficult. So we end up saying the angular size. Angular size of a galaxy. All the surveys will tell you the typical angular size, that's a measured quantity. You infer this angular size, assuming that you know the distance to it, and assuming a cosmological model, and you know its physical distance of the source, actual size of the galaxy. Okay. About cosmological model. So this is not a circular argument, because see, suppose I want to measure size of a particular that clock from here. End of the day, my eye is going to measure the angular size. And if I know the distance to it, I can get an estimate of that size. Now the question is, how well can I get this distance? This depends upon your underlying cosmology. For the far away galaxies. So we always measure something which is in the angular space. We call it and this distance we call it the angular diameter distance.
No, but
how do you get that distance? How do you estimate?
You don't estimate. So given a cosmological model and the redshift of that source. So think about it this way. Distance and redshift are related by some parameters. I know these parameters say at 10% level.
No. My question was, when you show the redshift, the definition you wrote, you say that denominator you cannot know. We cannot measure
that's H0 thing.
Yeah. So you say the denominator length you cannot measure precisely, but later on you show the black hole you will measure precisely.
Oh, okay, no. Okay. So that distance is the distance from us to that source. It is not the distance of the galaxy.
No.
It is how far the galaxy from us.
Yes.
And this is a very, very difficult quantity to know cosmology independent way. And that is what exactly gravitational wave enters. Because what gravitational wave tells you that when two objects are falling towards each other, how fast they are moving, this is by GR. Okay. And the amplitude of a signal also depends on the mass of the signal. So if I take a combination of how fast they are moving and the amplitude, this gives me a measurement of the distance. In the very simple way. This is what is done in 1986 by Bernard Schultz. But masses, that's the important thing. For masses, it's very easy to understand. If I give you two objects which falls towards each other, heavier objects falls faster.
Yeah, okay. That's
it. You see for a signal, is it moving faster or moving slower? And this moving part, we call it chirping in the gravitational wave. How fast frequency is changing. And that's what you'd like to do at the mass.
If I allow a second question. So still now I used to know that from black hole nothing come out, but you say that after merging, even though it come out. So what the
So
physics?
good, very good. So I will tell you something. It doesn't come out from the black hole, but we end up inferring the property of the black hole or the orbital energy releases from the observations. Still, nothing practically comes out of the black hole. So black holes itself are naive objects and very selfish to give you anything. No, so here, yes, so this says nothing, this says nothing, but when it moves from here to here, that's the amount of energy released, and that is unfortunately the black hole has to give away, is orbital energy, and that's the piece you call it the gravitational wave. Not, yes, outside the black hole, not inside, yes. But there is a very interesting paper which has come out, just want to comment on this. There's a very interesting paper come out by Kerr on Kerr black hole, that there is apparently no singularity. And I want to really read that paper and understand it better. It has come just during the winter break I was taking, so it's still on my to-do list. But just to point out to you that there is some nice theory was going on in that sector.
I have a very naive question. So you state that you have two black holes of mass M1 and mass M2.
Yeah.
Then there's the merger.
Yeah.
And the merged object is not smaller in mass than the sum of M1 plus M2?
They are, because some of the energies are gone.
So the merged object is lighter, right? Because
Right.
of the gravity.
M1 plus M, sum of the two
Therefore,
is...
some of the mass of these black
That's
holes
correct.
has come
Precisely.
out by
Yes.
the gravitational wave. I think that's the
Precisely.
question.
Whatever is the net black hole after merging, that mass is less than the mass of individual. Perfect, surely. But we end up measuring these individual component masses, let's not talk technology, some jargons, this M1 and M2 individually very well. That's because of the reason I told you, how fast they fall.
You talked about the CMB S4 experiment.
Yeah.
Now for the pulsar timing array, the poster guy is supermassive black hole merger, right? Now, what kind of gravitational wave, what is the kind of gravitational wave that is going to be measured by CMB-S4? And the second part of the question is, if the frequency is so low, 10 raised to minus 17, 10 raised to minus 18 hertz, does that also, what kind of challenges that low frequency pose? Do we need to observe for a long amount of time to get a
good
measurable?
So let's take it, you have asked me 3 questions. First is, what is the source? So as you go to this, this side, I told you the objects are smaller. This side, the objects are bigger, correct? This size, I'm talking about objects at the scales of the universe size. What is the source of it? The interesting part is, when universe is very, very small, or anything is very, very small, we start in the quantum regime. And the quantum fluctuation is inevitable. Quantum fluctuation gets imprinted on the sky and gets stretched very fast, so that we don't have time to respond. And this very fast part is required, we call it inflation. That means any fluctuation I give you, one of nature, it will generate scalar, tensor, vector, everything. You can show vector will decay off, scalar and tensor will be the successful one. Scalars are all the big objects, galaxies we are seeing, and tensor is the gravitational wave. This is your source term. Having said so, there is only one kind of source. If you are a particle physicist, you have a plethora of sources which can produce a stochastic gravitational wave background at different energy scales. That's another aspect which you can prove. Basically, the way to think about it, when universe is small and early time, it is hot. We are talking about energy scales which are large. So if I can go and measure those gravitational waves at those energy scales, I am basically probing physics at those energy scales. So that's equivalent to a linear detector you have on the sky. Now talking about challenges. Yes, it is challenging, but we are not going to do interferometer measurements there. What we are trying to do, we are trying to measure a pixel temperature with an error tens of nanokelvin. Okay. And we want to measure at a degree scale, do we have a signal or not? That means I need a better angular resolution, which is better than 1 degree. And I need a sensitivity, which can, is like a thermometer, which can measure sky temperature in 1 part in 10⁹ nanokelvin. With this in hand, now what I can do, go and ask on the sky, is the sky polarized? So everybody who has done a course on black body knows that there are so many scattering going on, it cannot be a polarized sky. But there's this interesting aspect that universe is expanding. It's slowly and slowly expanding, atoms are forming, and to the very few second last scattering gets and the last scattering gets imprinted on the sky as a part of polarization. This is something very simple, Thomson scattering. So this I'll be covering in my Astro 2 course, which I'm taking this time as well. So this will be observable on the sky. So what you want to do? Go to the sky, see signals at 1 degree scales. Are they polarized or not? Are they polarized in inducing scalar perturbations or tensor perturbations? This is a technological term. But bottom line is that you have a template of tensor perturbation, or you have a template for gravitational wave polarization. You want to map that with the sky. That's what you want to do.
This 10⁻18 hours that you're talking
Yes.
about. So how long? I mean,
no, it is not in. Yeah, good. So yeah. So what we are trying to do, the technology is now different. We're measuring temperatures. We have bolometers. We push the bolometer to the technology limited sector. We have the best bolometers available on Earth. It's not sufficient to give you 1 part in 10⁹ signal. Then what you do? You combine them. You combine few millions of detectors. You make array, and you get win by square root of those detectors. So you now the iteration time, we expect to get to this measurements like 2 years, 3 years, 5 years of iteration time. It is like square root of t. But you add many detectors in multiple channels, and you observe the sky.
Yeah, maybe I'm wrong. I thought you can see the photons only when it is the universe is for about 400,000 years old.
Yes.
Only after that the photons become free, and those are the ones.
Yes.
Well, earliest you can go.
Yes.
Yeah.
Not earliest. You can go a little more deep. There's something called as spectral distortion. So I have talked about fluctuation spatially. Because of physics of scattering between photons and electrons. Rishi is the expert on this. He works on that, Rishi Khatri. He will tell you, no, we can go a little more deep and can measure the thickness a bit better. But beyond that, it becomes optically completely thick. Yes, but gravitational wave is not. That's why I was saying that it's really neat to go much deeper because they don't scatter much.
Based experiments, you have the wavelength of the gravitational wave, which is what, kilometers?
For ground-based, this sector, yes, correct.
So, what is the shortest wavelength gravitational wave that you expect to see?
From ground-based?
From any base, I mean from all these origins, what is the shortest wavelength that you expect to see?
So, what is the boundary? The boundary is physics or engineering. There is something called as megahertz gravitational. We are in a position to, I mean, I've been discussing about this with some of the TIFR faculties as well, that if we can make an array, now you have told highest frequency, so your small size is fine. I want to do a tabletop experiment, not tabletop, but big tabletop experiment, where I can control each object's in momentum or position very well. Now, if gravitational wave is passing by, it will change the lattice structure a little bit. And that is your megahertz of gravitational wave. Do we have a science case? The answer is yes.
So there was, long back, I remember there was some attempt by cooling huge masses to millikelvin temperatures and then trying to look for small deformation.
Yes. That is not very good way.
It's not.
That has moved. So now the frontier which is being moved, if correct me if I'm wrong, it is a year back news from Fermilab is pushing this idea about getting to a tabletop cold system experiment. It's technically is extremely interesting, which maybe possibly we can also do in India, is a system of extremely controlled lattice, where you know the spacing very well. And if I deformed a bit, it's cool, it's cold enough. So if I deformed a bit, I know it's because of gravity. And then you make a coherent detection.
So mechanical lattice or a lattice, atomic lattice?
It is open to a lot of technologies. People are trying to open this up, and there are now seed funding. That's a good thing. So a lot of people are trying to, who are in the technology side of LIGO and all, now pushing their next challenging part, which is megahertz detector. And just to complete why the scientific it is interesting, it's a great probe for high energy physics, for dark matter, and so on.
Okay. Well, Suvodip, that was fantastic. Thank you very much
for
for a wonderful colloquium. And thank you all for sticking to the last portion of it. And we can all go together now, taking Suvodip outside the room. Otherwise, he'll keep talking. And have some snacks and tea together, please. Thank you, Suvodip. And thank you. I want to thank the audiovisual staff. Thank you.